Hello, I am presenting today a measurement of fine particle fraction during simulated adult breathing with a Nephele mixed inlet and laser diffraction with simultaneous drug dose analysis, the latest part of my research towards a more realistic method for measuring nebulized aerosols. My name is Lois Slator, a senior aerosol scientist at Philips Respironics, and I am presenting on behalf of my co-authors Owen Curry, Marcus Hilkemer, and Dara Manane.
There is shared ambition in industry to design more clinically relevant in vitro tests for nebulizers and other inhalation devices, with the hope to demonstrate bioequivalence using in vitro data and to refine the predictions of in vivo behavior. The proposed test setup is shown here with the airflow directions shown in red. The Nephele mixing inlet is used to introduce an adult breathing pattern from a breathing simulator to the test system, whilst maintaining a constant extraction rate required by a cascade impactor for measuring the droplet size of aerosols produced by nebulizers under simulated breathing conditions. Previously, Spencer et al. Measured the aerosol particle size distribution of nebulizers using an Nephele mixing inlet with an NGI and found that the fine particle dose, FPD less than 5 microns, decreased to 72% of that calculated by the pharmacopoeial method. The authors previously found that the fine particle fraction, FPF less than 5 microns, measured by laser diffractometry, did not significantly decrease when the Nephele mixing inlet was used compared to the continuous method. This work aims to investigate the relative importance of the contributing factors of the particle fraction and delivered dose to the difference in fine particle dose observed by Spencer et al. 5 Inspire-Go mesh nebulizers from Respironics Respiratory Drug Delivery nebulized salbutamol sulfate solution at a concentration of 5 mg per 2.5 ml for 3 runs. The volume median diameter, VMD, and fine particle fraction less than 5 microns was measured by laser diffractometry using a spray tech from Malvern Panalytical. At the same time, the drug delivered to filter was captured and quantified by validated HPLC method. Let's take a closer look at the test setup. In the continuous flow method, there was 30 litres per minute extraction through the inhalation cell, and a measurement period of 30 seconds was captured. In the simulated breathing method, the extraction was maintained at 30 litres per minute through the inhalation cell, but now the Nephele mixing inlet was used to introduce an adult breathing pattern with a tidal volume of 500 millilitres, an IE ratio of 1:1, and a frequency of 15 breaths per minute. 30 litres per minute of make-up air was also introduced. There was a 60-second measurement period. The extraction flow rate was set to 30 litres per minute, as it must be greater than the peak inspiratory flow rate of approximately 24 litres per minute for an adult breathing pattern. The sampling time during the simulated breathing method was doubled to 60 seconds, compared with the corresponding duration for the continuous flow method, to enable similar amounts of drug to be delivered to the sampling area, as aerosol was only collected during the inspiratory phase of the breathing simulation. The VMD measured by the spray tech increased in the range of 0.02 to 0.14 microns from the continuous flow to the simulated breathing method. This increase was consistent with previous observations. As the VMD and the fine particle fraction less than 5 microns are inversely related, it is not surprising to find that the fine particle fraction less than 5 microns for the simulated breathing decreased to 95.0 to 99.2% of that recorded for the continuous flow method. As each device was tested under both conditions, a paired t-test was performed, which gave a value of p equals 0.011, and therefore the change in fine particle fraction was found to be significant. The delivered dose for the simulated breathing method was found to have significantly decreased to 79.9 to 95.7% of the delivered dose recorded for the continuous flow method, p equaled 0.009. Fine particle dose less than 5 microns was estimated by multiplying the fine particle fraction less than 5 microns and the delivered dose captured on the filter. There was a significant reduction in the estimated fine particle dose less than 5 microns with the simulated breathing method to 78.0 to 91.2% of that observed with the continuous flow method, p equals 0.002. This graph shows the mean percentage reduction in fine particle fraction less than 5 microns, delivered dose, and fine particle dose less than 5 microns between the continuous flow method and the simulated breathing method, with the error bars showing the range of the results. The outcome indicates that the reduction in the amount of drug delivered was the greatest contributing factor to the reduction in the fine particle dose less than 5 microns previously reported. In summary, the use of the Nephele mixing inlet to introduce an adult breathing pattern for the assessment of particle size distribution during simulated breathing resulted in a small decrease to the fine particle fraction less than 5 microns, but a much greater decrease to delivered dose, and therefore reduced the fine particle dose less than 5 microns. This suggests that the focus of further research should be on the method for drug collection rather than particle size distribution. Thank you for your attention.